Welcome to problem 10. I actually was ready to restart recording a few days ago, 2 days ago, but then I realized that I had no idea at all. What I wanted to do was to use the same method as in problem 9, starting with this automorphism, but with this condition, sometimes square root minus 1 lies in k in f cubed, and sometimes it doesn't. So I didn't know what to do, and I was ready to start recording and had absolutely no idea. Then this morning I thought a little more about the problem, and it turned out that this is not at all a homomorphism. On this curve, we need to make another one specific for this curve, and the one we need, let's line over there, might look like this, where omega is a cubic root of unity, not unity. That means that omega 1 plus omega plus 1 vanishes. Right. One may choose plus minus y because a point mapping to minus the point is an automorphism, and the quotient group is just the group of two elements. But we have to prove that it's a homomorphism, that it agrees with addition. So what happens to the slope? So m of phi of the points it's one divided by omega times the old m, which equals omega squared times the old m. And in this case, it's the same. So this formula holds for this guy and for this guy. And that's the sum of the two. It becomes omega minus omega x1 minus omega x2 plus omega to the fourth of m. These indices should not be there. So it's omega times x3, and in this case the same. So this is actually a homomorphism, and it's obviously an automorphism. And that means in the algebraic completion of HQ, there are at most n squared points of order n, And now the same reasoning as I used in problem 9 to show that there cannot be n squared. I need to prove that omega doesn't lie in FQ. That is, FQ has only one cubic root of 1. But we need, of course, this guy to be an elliptic curve. And what's the condition for it to be an elliptic curve? Was it sufficient that Q equals 2 modulo 3? Actually, this should be the prime. Q is a prime power, so this should be the prime. There's only one cubic root of A, meaning there's only one point of order 2. Interesting. And then unit the point at infinity, giving 2 points altogether. So this must certainly just be the prime of which Q is a power. Now, it's obvious, because we already know that because of this condition, when then, you can't say that. There's only one solution to the equation x to the third, exactly one solution. And we already know that, unity itself, and that means that, now what is it, -1 plus square root, I've forgotten which it is, square root 3 halves, does not lie in FQ. It only lies in the algebraic closure. And therefore we can have at most n points of order n. And I believe that for all orders, there's only one point of order 1, only 2 points of order 2. I don't know about order 3, but it should be a general statement about this. So my idea of this morning worked as I had hoped it would. Thank you.